Hello, welcome to my talk on thin airfoil theory for cambered airfoils. This talk continues the last talk on thin airfoil theory for symmetric airfoils, and to extend the theory to the more practical airfoils, the cambered airfoil. Generally, the cambered airfoil could provide more lift, and this can be found in some natural wings, such as the wings of birds. In this talk, we will see again the importance of the mathematics, and we will see how we can use the mathematical tools to solve the complicated problems. In the first two slides, a summary would be made for the solutions to the symmetric airfoils, and on which we will show the method can be extended to the cambered airfoils. The general equation for the vorticity strength gamma z would be given for the small camber in small angles of attack, and this is the equation we are aiming to solve in this talk. But here, we show the solution for the symmetric airfoils first. For the symmetric airfoils, the mathematical equation can be reduced to this equation because there's no camber for the symmetric airfoils. And use the coordinate transformation for c and theta. So we have the relations for dc and the transformed leading and trailing edges, theta equaling to 0 and equaling to pi respectively. So use the coordinate transformation, the mathematical equation becomes as this form, and the corresponding CUDA condition would be given by this equation. For the symmetric airfoils, the vorticity strength can be given in this formula, and this vorticity would satisfy the CUDA condition, that is, the vorticity at the trailing edge is 0. Then the lift would be calculated as this and given as this. Here, the integral is actually the circulation around the airfoil. So the lift coefficient is given by this very simple form, 2 pi alpha. Here alpha is the angle of attack, see here. The moment with regarding to the leading edge is calculated as this, and the corresponding coefficient would be given as this and this. The pressure center can be decided using this formula, so we can see the pressure center xCp is at quarter of chord. This pressure center would be coincident with the aerodynamic center, which is at quarter chord, since the moment with regard to the quarter chord would be 0, a constant, which is the definition of the aerodynamic center. For the general equation for the vorticity strength, if we apply the coordinate transformation, we could have the vorticity equation as this, and the corresponding CUDA condition would be given by this equation. Following the solution for the symmetric airfoils, the vorticity gamma theta is given as this. Therefore, for the cambered airfoils, the solution can be extended, given as in this form. Here, the first term on the right-hand side is very similar to the solution for the symmetric airfoil, with A0 here replacing alpha here, the angle of attack. And the second term is the term of a Fourier series. From the expression of the vorticity for the Cambered airfoil, we can check the condition at the chilling edge when theta equals 2 pi. We can see the first term would be 0, as we have shown for the symmetric airfoil. And for the second term, it would be 0 when theta equals 2 pi. So if we substitute the new vorticity into the left-hand side of the equation, we have the expression as this. The first term would be very similar to the case for the symmetric airfoil. The difference would be A0 here, replacing the angle of attack alpha. And the second term would be more for the Cambered airfoil. Use the integration identity from the reference. We can have the result for the first term, simple as this. And for the second term, we can use the trigonometric relation. So the second term would be separated into two terms in this large ellipse. So again, we use the integration identity. We can obtain the expression for these two terms as this. So we put the last two terms together, we have the expression as this, and then the trigonometric relation given as this. So finally, we will have the expression as this. And if we apply the left-hand side term, we have this. Therefore, we can rewrite the equation in this form. This is the equation for building the relation between the camber line and the coefficient A0 and AN here. For getting the coefficient A0, we can perform an integration on the camber line gradient dz over dx here. So the integration from 0 to pi. So apply the relation here. So if we separate the integrand, we have the expression as this. And the last term would be 0 if we look at the relation. So here we exchange the order of integration and the summation. So the integration would be 0. Therefore, this term would have this result. We can deduce from this relation A0 can be expressed as this equation. And for AN, we can perform a manipulation, the integration from 0 to pi for the chamber gradient dz over dx times cosine m theta 0. Here m, it's an integer. So we have the expression as this. And we separate these two terms, the integration into two terms. So we have the expression as this. Obviously, this term would be 0. And for the last term, we can change the order of the integration and the summation. We have the expression as this. So here, we can see for the integration, only when n equals m, the integration would be non-zero. And this expression shows when n equals m, it is pi divided by 2. When n is not equal to m, the integration would be 0. So this term would be simply given as this pi divided by 2 times an. So this is the result for n equaling to m. So based on this, we can deduce the coefficient an given by this equation. So if we compare the result for symmetric airfoils, since for symmetric airfoils dz over dx would be 0, hence we can see a0 would be same as alpha, the angle of attack, and the an would be 0. So when we obtain the vorticity expression, we can calculate the lift acting on the airfoil based on the Kuta-Yukovsky theorem. Here, the integral is the circulation around the airfoil. So if we substitute the vorticity expression and the coordinate transformation, we have the expression as this. And for the first term, it would be very similar to the case for the symmetric airfoil. We have the result as this, and the second term would be this. So now we apply the relation given by this. Here, the integration is non-zero only when n equals to 1. So we have the result as this, and together we have the expression as this. Now if we substitute a0 and a1 into this result, we have the expression as this. If we write the lift in a form as this, here alpha 0 defined as this is the angle of attack of 0 lift for the Cambered airfoil. The lift coefficient is given by this, and we can see the slope of the lift coefficient is 2 pi. This is the same as the symmetric thin airfoil. Then why the Cambered airfoil can provide more lift? The reason for this is because for the Cambered airfoil, we have a negative non-zero lift angle of attack alpha 0. So that means for the same angle of attack, Cambered airfoil could provide more lift for the airfoil. Here we look at the aerodynamic moment m0 with regard to the leading edge, which is calculated as this, and use the vorticity expression and the coordinate transformation. We have the expression as this. So we can see the term in this bracket is from the vorticity expression, and here is from the coordinates xc, and this would come from xc and all the constants we put together here. So now we separate this two terms into these two terms here, and use the trigonometric relation. We have the expression as this, and here we exchange the order of the summation and the integration. So we have the result for this first term, and for the second term, we again separate this into two terms. So we have the expression as this. Here, the trigonometric relation, this is used for this term. And again, we look at the integration for this term and this term. Here, for this term, when n equals 1, it is non-zero, given by pi divided by 2. Otherwise, it would be 0. And for the integration in the last term, we can see only when n equals 2, the integration would be non-zero here. And when n is not equal to 0, it would be 0. Therefore, we have the expression for the moment with regard to the leading edge given by a result as this. So we can calculate the moment coefficient Cm0 given by this, and the expression as this. Here we can see the moment coefficient Cm0 is decided by A0, A1, and A2, but A1 and A2 are only dependent on the camber line, while A0 depends on both angle of attack and the camber line. This means the coefficient of the moment with regard to the leading edge would be dependent on the angle of attack. Now if we calculate the moment at the quarter chord, mc divided by 4 is given by this expression. And we can separate this expression into two parts. The first part as this and the second part as this. If we look at the expression, we can easily see the first part of the expression is actually the moment m0, the moment with regard to the leading edge. And the term in this ellipse is actually the lift air. So we can simply express the moment with regard to quarter chord given by this expression. So if we substitute the m0 and the air into the expression, we have this, and finally have this expression. And we can now calculate the moment coefficient Cmc divided by 4 given by this. And we can see this moment coefficient is only dependent on A2 and A1. However, if the camber is given for an airfoil, so A1 and A2 would be constant. As such, the moment coefficient with regard to the quarter chord would be a constant. This means the quarter chord is the aerodynamic center. So this is the same as the symmetric airfoil. But here, the only difference is the coefficient for the cambered airfoil is non-zero given by this, while in the symmetric airfoil, the moment coefficient with regard to the quarter chord is 0. The pressure center XCP can be determined using this equation. And if we substitute m0 and L into this equation, we have the expression as this. So we can calculate the center of pressure XCP as this, and we can see this is the detailed expression. Therefore, for the cambered airfoil, we can see the pressure center and the aerodynamic center would be different, since for the center of pressure, we have the additional term given in this ellipse. Now, in the next few slides, two airfoils will be studied. These are two famous cambered NACA airfoil, namely NACA 4412 and NACA 23012. Both have the same maximum thickness, 12%, but with very different camber lines. For NACA 4412, the maximum camber is 4% of the chord at the 40% of the chord, while the NACA 23012 has a camber about 1.88%, and this maximum camber happened at the 15% of the chord. So we can see in this plot the comparison of these two airfoils. The black line for the NACA 4412 and the dotted line for the NACA 23012. And the red solid line for the camber of the NACA 4412 and the red dashed line for the camber of NACA 23012. We can see here NACA 4412 has a much larger camber than the NACA 23012. The mathematical expressions for the camber line are given as this. For NACA 4412, when x is less than 40% the chord, which corresponds to theta 1 equaling to 1.369 or 78.46 degrees. So the camber line has a mathematical expression as this. And for x between 40% chord to the 4 chord, the camber line is expressed as this. For NACA 23012, when x is less than 15% of the chord, which corresponds to an angle theta 1 equaling to 0.795 or 45.57 degrees. The camber line is expressed as this, and when x is between 50% and 100% of the chord, the camber line is given as this formula. In this slide, we examine the calculation for the NACA 4412. As we have shown in the previous slides, the lift coefficient is given by this formula, and the moment coefficient is given by this formula. Here, A0 is given by this, and AN is given by this. And the x and the theta has their relation by the coordinate transformation. So for the camber line of the NACA 4412, we have the expression as this. And we can calculate the gradient dz over dx given by this and this. As such, we can calculate A0 given by this, and we can calculate the integration, use the integration by two parts given by this and this. So basically, this integration can be done step by step by hand, and we can also program to get this integrals use a computer. It should be noted the calculation by hand is not an easy task, while the computer is really fast and accurate for doing this, and the result would be given as this. And for A1, the expression is as this, so we have two parts of the integral, this one and this. Again, we can do this by hand, but the computer program is easier for doing this calculation. We have the result as this. For A2, it's very similar to A1. The only difference is the integrand here, cosine 2 theta, rather than cosine theta. So the calculation would be very similar. Using the computer program, we can easily obtain the answer for these integrations with the result given by this. Having obtained all coefficients, thus we can calculate the lift coefficient given by this, and we can obtain the angle of attack of 0 lift alpha 0 given by this minus 4.15 degrees, and the moment coefficient is given by this minus 0.106. Here in this slide, the comparison is made for NACA 4412. This is the comparison for the lift coefficient from the thin airfoil theory and the experimental data. We can see the lift coefficient prediction is very close to the experimental data when the angle of attack is small. And the 0 lift angle of attack is predicted as minus 4.15 degrees, while the experiment data is 3.99 degrees. Both are very close. This is the comparison for the moment coefficient. The thin airfoil theory prediction gives minus 0.106, while the experiment data shows minus 0.095, quite close each other. For the NACA 23012, we can use the Cambered line to calculate the coefficients A0, A1, and A2 for calculating the lift coefficient CL and the moment coefficient CM. So the Cambered line for the NACA 23012 is given by the piecewise formula as this. And we can easily calculate the gradient of the Cambered line, dz over dx, given for this when x is smaller than 15% of the chord, and this for the rest of the chord. Accordingly, we can obtain A0 as this, and we can see the integral would be more complicated, especially for the first term here. Hence, a computer program would be easier for getting the result. Here we have A0 as this, and A1 is calculated as this, and this integral would be more complicated. But with the computer program, this would be easy enough. We can get the result for A1 as this. Similarly, for A2, the calculation is given as this. The difference A1 and A2 is the integrand A1 cosine theta and A2 cosine 2 theta. So the program would calculate the result for A2 as this. So based on the above result, we can calculate the lift coefficient CL given by this, and we have the result as this. Therefore, we can obtain the angle of attack of zero lift alpha 0 given by this. It is minus 1.1 degrees, and the coefficient of the moment at the quad chord is calculated as this, minus 0.0124. Here, the comparison is made for the NACA 23012. This is the comparison for the lift coefficient from the thin airfoil theory and the experiment data. We can see again the lift coefficient prediction is very close to the experiment data when the angle of attack is small, and the zero lift angle of attack is predicted at minus 1.1 degrees, and the experiment gives minus 1.25 degrees. Both are very close. This is the comparison for the moment coefficient. The theory prediction gives minus 0.0124, while the experiment data shows minus 0.01, very close indeed. In this slide, the summary is given for the thin airfoil theory. The advantage for the thin airfoil theory: the theoretical lift coefficient for thin airfoil is given by this formula. Here, CL0 would be 0 for the symmetric airfoils, and the slope of the lift coefficient given by this 2 pi for both symmetric and cambered airfoils. The aerodynamic center lies at quarter of the chord behind the leading edge for both symmetric and cambered airfoils. The importance of the CUDA condition is shown for generating a lift on the lifting bodies in inviscid flows. The disadvantages of the thin airfoil theory include it cannot include the effect of the airfoil thickness. It can only work for airfoils with small camber lines in small angles of attack. Thin airfoil theory shows no limit for the maximum lift on the airfoil. The theory cannot include the airfoil drag, especially the friction, due to the fact the flow is regarded as inviscid.